All right, it's 3:30. We can start.
Sure.
All right, so welcome to CSRC Colloquium. We're very privileged to have Dr. Damian Rouson here. He's going to be talking about some of the accelerated computing and parallelization aspects that are built into Fortran 2023. It's going to be a cool talk. And so, for those who don't know, Dr. Rouson is group lead at LBNL, and the Computer Languages and Systems Software Group. And I believe he works with the UPC Plus, right?
Yeah, my group developed UPC++. Yeah. So
and I know Johnny Corbino from here worked on that project too.
Yeah,
right?
exactly. Yeah.
Great. Are you going to be covering UCP Plus?
No, this talk will focus on Fortran.
Yeah. All right. Well, without further ado, Dr. Rouson, thank you.
All right, thank you. And so I guess we're scheduled for an hour, so I should probably plan to go for like 45 to 50 minutes. And
50 minutes, 10 minutes.
Okay, good.
Yeah.
At the same time, feel free to interrupt me along the way with questions. I can always talk fast, or if we have enough questions along the way, then maybe we don't need time at the end. So we'll see how it goes. How many of you have written any Fortran code or even worked with Fortran codes? Awesome. Okay. That's actually a much higher percentage than I would expect in most rooms. I guess most of exactly. I was just going to say that. I can thank Jose for that. Of those who have not written Fortran, how about C or C++, a compiled language? Okay, good. All right, so everybody at least has experience with using compiled languages. Probably, yes, you were raising your hand for the C or C++.
What about English or French?
I love that question. I oftentimes make the point that programming languages are human languages. We call them computer languages. They're actually human languages. If it was just about programming a computer, we could write ones and zeros. We could write machine code, right? And so the reason we write high-level languages is because they're closer to English, because we want to communicate with other people who need to read our code or communicate with our future selves, which, if you carry that far enough, has some really interesting implications, because you start to realize that once you realize it's a human language, you start to realize that some of the biases that can crop up in human languages can also crop up in programming languages. And Fortran is like the butt of so many jokes. And there's a whole other talk I wish I could give about like the sociological aspects of this stuff. But yeah, I compare it to English. And one of the members of my group, Kate Rasmussen, is a linguist by training. She has a bachelor's degree in history, master's degree in linguistics. And she has taken her study of linguistics and is now applying it to programming languages.
I have an English compiler.
An English compiler?
Yeah.
What does that mean?
It's got 1,000 words that are pronouns.
Very cool.
Yeah, and you type it in.
Awesome.
What's your name?
Damian Rouson.
Damian. It says, put Damian's favorite song into it, carriage return. And then it starts playing.
Outstanding. Okay, so even those of you who are familiar with Fortran probably don't know about Fortran 2023. That's the latest version of the language. Anybody in here have experience with parallel programming? Outstanding. Okay, so for those of you who've done parallel programming, how about OpenMP? Great. MPI. Outstanding. You won't see any of that in this talk. That's the point. So there's some of you might have heard the statement before that MPI is the assembly language of parallel programming. When I first heard that, I thought of it as kind of a joke, kind of a slam against MPI. Then I talked to Bill Bropp, who led the development of MPI in the early days. So for those who aren't familiar, MPI is the message passing interface. So you use it to write parallel programs that can work on 100,000 cores across a bunch of nodes on some supercomputer. And Bill said that was the point. It was intended to be an assembly language. The compiler was supposed to generate it. What happened was it took too long for parallel programming languages to come around. The computational scientists couldn't wait. They needed their codes to be parallel, decades ago. And so that's how we ended up with MPI in our applications. It was never intended to be this way. So what I'm going to try and show you is a different way to do the parallel programming, such that, and actually I won't go into a lot of detail about the actual parallel programming itself, because so much of it is happening under the hood for you, but in a way that remains efficient. So I'll talk about how it applies to high performance computing. So I usually use that term when I'm talking about traditional computational science areas like biosciences, the application we'll look at, or weather or climate. And I'll talk a little bit about how we use Fortran 2023 in AI. We had a family reunion in July, and my family asked me to give a talk on AI. So it actually gave me a chance to rethink my acknowledgement slide and acknowledge the ancestors, my parents, because they got me into coding. My mom sent me to a science center when I was 12, back in 1979. And that was where I first learned to code. And actually, Fortran was the first language I learned. Didn't actually write any Fortran again until college because my high school didn't have a Fortran compiler, and I didn't. And so I was, I guess, writing BASIC, and then actually some machine language. So I was actually writing hexadecimal code, basically, which is almost the exact same as assembly. It's like the lowest level, but at least assembly has some codes in it that look kind of like English, like LDA means load accumulator. But this was 1982. My mom was a journalist, which is the only reason we had a computer. She was using it for word processing. I didn't really know how to explain to her what an assembler was, and I didn't have money to buy one myself. So I had to write the hexadecimal machine code, basically.
Were you using it? Because I took Fortran way back then too, right over here. Did you have the punch cards?
So I have a memory that I have not been able to verify. My recollection is that, so no, I didn't use punch cards. My recollection is that I was on a screen that had 4 lines on it, but I haven't been able to find anything online that looks like that. So since I was on such a limited screen, I've always thought if I showed up any sooner, I would have been on punch cards, but I just barely missed the punch card era. So, okay, so do some background motivation, why Fortran matters, because some of you, well, that's what's so awesome about this audience. A lot of you already have used Fortran. Hopefully you didn't curse when you were using it. If I had to deal with most of the actual Fortran that's out there in the world, I wouldn't like Fortran so much either. So I'm trying to show a very, very different way to write the code. But for a lot of audiences, particularly in the US, okay, speaking of like human biases. So the first slide I'm going to show you is about like why Fortran matters. The first time I showed that slide, I was actually at a conference in Switzerland, and somebody raised his hand after the, or maybe during the talk, and said, "You don't really need that slide around here." You would be surprised how much more accepted Fortran is in Europe and in Japan than it is in the US. And I could relate that to all kinds of stuff about biases in the US, but we won't go there. Okay, so then talk about what I'm trying to do with the language. And then, time permitting, a bunch of open source packages that my group contributes to. Most of these we actually lead the development of ourselves, and conclude with sort of like when, why, and how we use the language. Okay, so why Fortran matters. Basically, I usually say that Fortran is used a lot in fields that embraced computing early. So if you were doing computing in the 1960s, Fortran was largely the name of the game, right? And those are fields like weather, climate, nuclear energy, aerospace. These are fields where you'll find lots of Fortran. If you're running on big supercomputers like we have at Berkeley Lab, our Perlmutter supercomputer, when it debuted about 4 years ago, was actually like the world's 4th fastest supercomputer. Running on systems like that, most of the cycles are actually Fortran. How many of you checked the weather forecast today? I guess the thing about San Diego is you probably don't have to check it. It's so beautiful. Pretty much every weather code is written in Fortran. So every time you look at a weather forecast, you're looking at the results of a Fortran code, like almost guaranteed. So think about all the countries that have signed climate agreements, and probably like something like 190 countries across the globe. They did that based on results of observations, data taken from observations, and the results of Fortran codes, right? So think about what impact that code has on the global economy and technology and what have you. So motivation. So there's a meeting I went to a little over a year ago. It was a bunch of nuclear science researchers, and it was a project that I was joining, a really big project. It has probably 30 or 40 people across the country at different institutions working on it. And I had been told before starting on the project that people were beginning to move away from Fortran in this community. And so as my first introduction to the community, I was asked to give a 15-minute talk to kind of like, this is sort of my sales pitch to maybe try and keep people, from abandoning the language. And so I titled the talk, "The Problem is Not Fortran." Okay, So the problem is not Fortran, that's my proposition, but there are some problems. So we have to talk about them. I think there are three big problems. One is perception. The most non-Fortran programmers, if they know anything about Fortran, it's usually based on Fortran 77 or at most Fortran 90, right? I'm going to jump down and say the state of the practice is also an issue. Even most people who are writing Fortran are writing Fortran 90 or 2003, right? So 2003, 22 years old. How many in this room are 22 or younger? Anybody? Are these all grad students? Okay, one. Fortran 95 is, Fortran 90 is 35 years old. How many in this room are under 35? 35 or under, okay? Yeah. I frequently tell people that if you're going to try to recruit people onto your project, you're going to have a very hard time doing it if you tell them they can't use any features that were developed within their lifetime. Okay, and that's what you're saying when you tell people to write Fortran 90 or 2003. Okay, I have a collaborator in this nuclear science community that I mentioned. He's a postdoc who was born in 95. He said to me at one time in a call, yeah, I took a look at it, but really don't think I need anything in the language beyond Fortran 95. I'm on the Fortran committee. We develop each new version of the language. And I said, that cannot possibly be true unless you think the Fortran committee has wasted your entire lifetime. Within 5 minutes, he asked me a question for which the only answer was a feature from Fortran 2008. By the end of that call, he mentioned his use of MPI, and specifically this module called MPI+X, which is actually misnamed because it's using features that are in Fortran. It's not using features that are in Fortran 2008. It's using features that are in Fortran 2018. So I was able to explain to him that that module you're using, the only reason that stuff works is because of features from Fortran 2018. So within the same call, I was at least able to jump him up to realizing he needed at least Fortran 2018. Right?
Is it like some kind of situation where the earlier Fortran, for lack of a better term, was so robust or did so much that as you guys have gotten more and more modules on it, there's just less applicability?
So I think I would put it differently.
I thought it would be like you described, just the opposite, that the new would be more useful.
I mean, I probably should be careful because I'm not a sociologist. So, but I would put it differently. I would think it's more of a sociological issue where the people who really wanted to do advanced software engineering started a good 20 to 25 years ago abandoning the language because it was, in some ways, it was taking too long for the language to catch up to certain things like object-oriented programming. Although, even so, I would say that in other ways, the language was really far ahead, and that story doesn't get told so much. So then what happened is you're left with people in the language who aren't as concerned about rigorous software engineering practices. They just want to write the code to get it done, right? So that's not the group that's going to adopt new things as it comes out. But there's also an issue with compilers. Since the beginning of 2024, I have averaged almost one bug report a week on a compiler.
Submitted 1 hour.
And this week is no exception. I found one this week, but there are solutions to these problems.
I would like to just chime in a little bit that I think you mentioned it, the difference between familiarity versus simplicity is buried under here, where people say, I just want to write Fortran 90 because it's easier.
Yeah.
Right? Or what it means is more familiar, right? Because you're using regular loops and things. And when we write code, you could call it Fortran 90, but it's really Fortran 90 plus the little things we cherry picked.
Yeah.
2018,
there you go.
2023.
There you go.
And put that in there
Yeah.
to do what we needed, to solve the solutions that we need. Other people who want object-oriented stuff, they're massively using the new features. So I think there's two categories.
Yeah. And because
the CUDA Fortran is at 2008.
Yeah.
Yes.
Yeah. So and that's
I put okay. 2003 plus a few things.
I'm talking to a big co-ray fan, so
yeah. So that's actually the approach that I advocate. Pick up the new features that you need. Use whatever features your compiler supports. If you're going to state a version that you're writing, I recommend just using whatever's the latest version. When you just say you're writing Fortran 2023. Yeah, and there's lots of reasons for that. One is that some of the advances are so obviously useful that why would you not? So for example, it used to be the case up until Fortran 77 that you had to write everything within 72 columns on the screen. So 72 characters across. And yeah, and there you go. And then in Fortran 90 that got expanded to 132. But these days, even that feels limiting. Fortran 2023 expanded to 5,000. You can write lines as long as you want, right? So if you write a line of code that is 133 characters long, you're either writing non-standard Fortran or you're writing Fortran 2023. So some of the stuff is so obvious that why would you not use it, right? So I say say you're writing Fortran 2023, but of course you're only using whatever features your compiler supports, right? So one of the problems that I talked about is perception, and that's because of outdated images of the language. And one of the things that most people think it's a dying language, right? I've had important people. I was talking to someone who's like a director at Argonne National Lab a few months ago who said exactly those words. It's a dying language. Fortran's a dying language. Well, you wouldn't know it if you look at the data. So data are our friends, right? So this is something called the TIOBE index. It's basically a measure of programming language popularity. And if you go back, Fortran peaked in 1990 at like the second most popular language, all right? Now, it's true, there was a long slide where you get to 2020 and it dropped all the way down to 31, right? How many of you know about Julia, the Julia programming language? Like the hot new kid in town, right? Which, by the way, it's been around for almost 15 years, so it's not so new either. And right now, Julia is at about 31. Okay, so that's where Fortran was at the bottom. And then it's actually come back, and over the past year and a half, it's been averaging right around 10. So there's actually been a resurgence in the popularity of the language. And I don't know the reasons for that, but I suspect if something's growing really fast and you're trying to figure out what's causing it, one of the easiest things to pick is what else is growing really fast right now? What else is growing? Exactly. And I can actually show you an article that blog post that someone just sent me a few days ago that was basically saying exactly this, saying, I'm back to running Fortran, I'm back to using Fortran because of AI, because like they found that their code was running 10 times faster just from switching from Python to Fortran.
Just to that point real quick, in the early 90s, I was on General Dynamics flight software team. We wrote software for the Atlas Centaur rocket, right. And we inherited it in Fortran. Yep. And they asked us to convert it to Ada. And it's not even up there.
Right.
And so at the point, they thought, oh, this is old, this is no good anymore.
Exactly.
So they re-taught us how to do everything in Ada. We reconverted it all. And I really didn't like Ada personally, but it was very Englishy.
Yeah.
And it's not even up there. So
exactly.
To your point.
Yeah.
Java was at the rate, sort of like a derivative of Ada. Or that's my opinion.
It's
so
long ago.
How much of that popularity index do you feel is because of choices of the university system nationwide?
Oh, it has so much to do with
what
that.
They teach under lower division, upper division, graduate.
Oh yeah.
I was a CS major undergrad, and it was all Java for the first 2 years, all C++ for the second 2 years. We never even knew Fortran existed except in one class where we learned like Prolog and these other old languages, and it's like then you hit graduate school, it's like, oh, Fortran. So it's like if people were to teach Fortran from the get-go, I think it would be much higher on the list.
Yeah, exactly. And a lot of that, what's being taught is driven by funding. So like, the National Science Foundation, if you look at the kind of research grants that they fund, it's always got to be revolutionary, right? If you're advancing an old language, that's evolutionary, it's not revolutionary. So of course, all the professors who are going after grants, they're going to develop the next new language that's going to be the greatest thing, right? Like, it's really hard to get.
I think another aspect is that, like in the CS department, for example, a lot of those graduates are going to go possibly to places like Google, Facebook to write, application code, which is almost never written in Fortran, right? It's sort of like more of a scientific language. In the sciences, so they sort of just like, well, we're just going to teach C++ because that's what they're going to use. We'll use it across the board.
Yeah.
And they just sort of wiped over the Fortran part of the sciences
Yeah,
because
exactly.
of that, I think.
I think you had raised your hand.
No.
Okay, sorry.
Agree with.
Okay, so what are the solutions? Data is one. I just showed you the TILB index. Better compilers is another. So my group contributes, we're actually funded to contribute to the LLVM flying Fortran compiler. So this is one of the newest open source Fortran compilers. And it was launched by a Department of Energy funded worldwide public-private partnership. Over half of it, at least last time I checked, was written by NVIDIA. My group is collaborating with people at AMD who are actually in Germany, and with a company called Cyperl that's in France. Big community, ARM, all these different companies are contributing to LLVM flying. It is rock solid. So when I mentioned that I submit about a bug report a week since the beginning of last year, at most one or two of those run flying. I've submitted so many bug reports on. I've wasted years of my life almost writing Fortran bug reports, and so I would love for people to check out flying. What I would say is that in terms of feature support, it is already on par and even ahead of a lot of other compilers. Not necessarily yet in terms of performance. I have seen some cases where it generates much slower code. So that's not every case. So I say at least try it and see how it works for you. Specifically, we've been working on the support for do concurrent. It's a loop level parallel construct. So that's what basically gets translated to OpenMP, right? Just like I was saying that there's a bunch of features that replace the MPI. It's not because the MPI isn't there at all. Depending on what compiler you're using, there's still be MPI under the hood. And with do concurrent, right now there's OpenMP under the hood on with Flang. One of the nice things though about not having to write your own OpenMP is that OpenMP isn't the only option. Right now, Flang will take do concurrent and translate it to OpenMP, but there are people who are talking about working on an option to instead translate to OpenACC for running on accelerators, GPUs, right? And the same thing like with the multi-image features. An image is think of it as a process, or if you're an MPI programmer, a rank, right? And so the multi-image parallel programming, if you're using Fortran, they're supported by MPI. If you're using Flang, they're supported by GasNet, which is developed in my group as well. It's networking middleware. Think of GasNet as being like MPI, but stay true to its original purpose, right? Again, the purpose of MPI was not that you would ever write it. It was that the compiler would generate it. You will never see calls to GasNet in any application. It's always somehow under the hood, and there's a layer between you and GasNet. In this case, the layer is the language, basically the compiler, right?
I don't mean to interrupt, but you asked us to.
Yeah.
Just maybe you could mention that Flang, if you go Google Flang, there's many Flangs out there. There's like the old Flang, there's the new Flang, there's this Flang, there's the AMD Flang.
Oh,
when you say Flang, which Flang should we be going to for this rock solid compiler?
Yeah, I didn't explain why I was saying it, but this is why I always say LLVM Flang, because as you said, there's an AMD Flang, there's all these different ones. There's a lot of history behind that. You could almost say there have been two LLVM Flangs, because there was one that was started that was abandoned and had to just get rewritten from scratch. So I'm talking about LLVM Flang as it is in the current LLVM project repository. Chris.
Does LLVM Flang also support GPU offloading?
So we're working on that. Well, okay. With OpenMP, I think the answer is yes.
OpenMP supports offloading, but does the Flang interface to OpenMP also allow offloading onto a GPU?
And when you say the interface, you're talking about do concurrent?
Well, I guess that gets mapped to using the OMPI library, so that's running on CPU threads.
Yeah.
But
so
in OpenMP, you can do GPU offloading, but is there like an API or an interface in Flang that does the offloading of the GPU?
Okay, there's sort of two answers. One is it supports OpenMP, and you can do offloading with OpenMP. My understanding, and I'm actually just corresponding with some people about this today, so I haven't gotten an answer yet, partly because they're in Europe, so I probably won't hear it till Monday. I'm pretty sure it supports OpenMP 5.0, which includes the offloading, and they're already working on OpenMP 6.0, which is the latest, right? That's if you're writing your own OpenMP. Now, if you're writing do concurrent, again, like I was saying, like one of the nice things about putting this stuff under the hood is you don't necessarily have to make a decision when you're writing the source code about whether it's going to run on the CPU or the GPU, right? So as of right now, The latest release, Flying 21, which just came out around maybe 3 weeks ago, it can parallelize do concurrent on the CPU, but I'm working really closely with the compiler engineer at AMD who's working on offloading do concurrent to the GPU. And he's already submitted enough, pull requests that, I can, my speculation, since I'm not the one who's doing it, I can't promise it, but LVM releases twice a year. So the next release is, less than 6 months away. My speculation is that by LVM 22, you'll be able to automatically offload do concurrent, and you won't even have to write OpenMP or OpenACC or CUDA. Yeah.
The AMD Flying grant, fork or whatever of LVM Flying claims to do it for AMD GPUs. I haven't gotten it to work, which is one of my bug reports. But they have implemented it on AMD Flying, which then will be pushed back into this Flying once it's ready, guys. So
It only works on Instinct, right? It doesn't work on NVIDIA GPUs.
No, well, they're
not
translating.
AMD Flying, but but NVIDIA is going to switch over to Flying soon.
Well, again, they're translating to OpenMP, right? So it should work anywhere. It should work on any GPU that OpenMP supports, right? And also the multi-image features. I need to update this slide. This is from a few months ago, but the first multi-image features are there now too. So I can say for sure when LVM Flying 22 comes out, you will now have both the replacement for MPI and the replacement for OpenMP. You can just write Fortran, right, and do distributed memory, parallel programming, offloading to GPU, what have you. Okay, let's move on. Okay, so what am I after, and why am I here? So I had this vision for how to do parallel programming that goes back almost 25 years, I think. I became a professor at the City College of New York back in '99. I was there for about 5 years, and then I've moved around a bunch since then. And my training is all my degrees are mechanical engineering. I did my bachelor's at Howard in 1989, master's and PhD at Stanford, finished my PhD in '97. And the idea, then I was working in Silicon Valley for a couple of years in consulting, and '99 I became a professor. Started thinking about writing your own code. And I was doing computational fluid dynamics, and I had this idea that I wanted to make representation of partial differential equations, PDEs, more closely resemble what you see in a textbook. So, because I often say that if you look at a CFD, computational fluid dynamics package, software package, take someone who's like a junior in undergrad, just took a course in fluid mechanics, they've seen the Navier-Stokes equations, march them over to a screen for a CFD code, they will not see anything on the screen that looks even remotely familiar. Okay, it doesn't have to be that way. So what I'd like to do is develop software abstractions that resemble continuous mathematical abstractions, including the operators, div, grad, curl, right? And the thing I love about collaborating with Jose is that I think what Jose and his students and collaborators have been developing is what's going to finally enable me to achieve this in the way that I really want. So there's a technique that Jose develops, mimetic differences. And basically, actually, he just gave me this phrase, discrete calculus, earlier this week. It's the perfect way to summarize it. What you're basically doing with mimetic differences is you're defining a discrete calculus. Okay, and so just like when you're doing multivariable calculus and you learn about divergence, gradient, curl, but you're applying those to continuous functions, and you expect certain properties to be true. Like in your multivariable calculus class, you learned about Green's theorem and Gauss's divergence theorem. Well, it turns out, dirty little secret, a lot of numerical methods don't preserve those properties. You don't get those integral theorems that you expect. And that means you don't get things like conservation of mass, conservation of energy. And that's why codes blow up. They give you really, bad results in certain circumstances, right? What happens with mimetic differences is the discrete equations that you're working with satisfy a discrete version of those integral theorems, a discrete version of Gauss's divergence theorem and Green's theorem. And so you get much better properties for the behavior of the computation. And Fortran 2023 means that I can implement those in a way that's parallel, including automatic GPU-based acceleration, right? Which, okay, this part is coming soon. But not quite there yet, but, well, actually, yeah. Don't get me started. I abandoned the video compiler in 2004. I remember it well, because by that point I had already begun submitting a lot of compiler bug reports, and I had learned that if you want to get a compiler team to pay attention to your bug report, you need to reduce it down to the smallest minimal reproducer you can that shows the problem. I try to get it down to 15, 20, at most 25 lines of code, right? Because if you do that, you're shining a laser on the issue. I've submitted bug reports this year to the Fortran developers, where literally the same day, within hours, somebody came back with a patch to fix it, because it just makes it that clear, right? There was so NVIDIA bought a company called Portland Group. So the NVIDIA compiler is the Portland Group compiler. Uh-oh, it says connecting. Oh. Hopefully this will come back. Where's the guy who helped me? Oh, you. Do you have any idea what's happening?
Yeah. Exit.
Exit? Okay.
In the presentation.
Not letting me. Ooh, I guess maybe my computer, because the computer went to sleep. Okay. I think I know what to do about that. I have a software package called Caffeine, which if you turn it on, hopefully it's going now. It keeps the computer awake. Darn it, I can't tell if it's running though. I need to get back on the network now too. Okay, I'll join, yeah, I'll have to rejoin Zoom. Okay, now I'm sharing. Okay, great.
Fortran 66.
Okay.
I thought that collection.
Make sure I click more often.
Fortran 66.
I have more.
Okay. All right. So I published a book called Scientific Software Design that came out in 2011, and it mostly focuses on object-oriented design patterns. So design patterns are basically best practices in choosing what classes to write in object-oriented code. And I had something in my book called the abstract calculus pattern. And this is sort of an example of it. And so what I was saying was the dream was to write PDEs in a fashion that looks, like you'd see them in a textbook, basically, right? So this is not pseudocode. This is compilable Fortran syntax. All right. And given that this is CSRC, there's probably a lot of people in the room who know what the equation that is. So go ahead and say it, whoever sees it first. What equation is that?
Conservation equation.
Okay, yep. Chris, I forget, what's your field? Is it physics? No.
I'm in electrical engineering.
Ah, shoot. Okay, I should have put up a different one up.
Hydrodynamic.
Okay,
It's not the Darcy law, is it?
No, hydrodynamics. So what's the main equation of hydrodynamics? The Navier-Stokes equations. Yeah, exactly. So this is the Navier-Stokes equations. Okay. So depending on the audience, a lot of people would get it. But either way, at least one person got it, right? That's really expressive power when you can put something up and people recognize it. So if you have, those of you, who have studied fluid dynamics, this is much closer to what you saw in a textbook than, what you'd see in most computational fluid dynamics codes. And so the idea here is that I have these quantities, like this is a velocity and this is the pressure, density, and I want to be able to do things like compute a gradient of the pressure and a Laplacian of the velocity, right? And things like dot product, right? And so the ampersands here are continuation characters. In Fortran, if you go to a new line and you want to continue the same statement, you have to put a continuation character. So this is what it would look like if you saw it in a textbook, okay? So hopefully you can see the correspondence there.
From optimization point, the divide by row is glaring at me, but that's okay.
Oh, yeah, that's true. That should probably just be absorbed into the P. So what he's saying is that this is constant. So these are variables of 3D space and time. But this is what's called the incompressible Navier-Stokes equations. Incompressible meaning the density doesn't change, it rose the density. So since this is a constant, I probably should have just absorbed it into the P. So
more the division rather than the multiply by the inverse.
Yeah.
Either way.
Okay, so the idea is that if anybody's familiar with functional programming languages basically make programming more like math. Not necessarily in this exact sense. It's more like in the sense of when you write y equals f of x. If I tell you x is 2 and f is quadratic, f is, then you can calculate f of x. And if I come back and say what's x, you'll still say it's 2, right? Because in math, you don't imagine that computing f of x changes x. Whereas in programming, you could call an f of x that will change your x. It makes the programming very non-intuitive, right? And so this is what I'm getting at here is that there's a way to adopt a functional programming style in Fortran. Functional programming centers around pure procedures, and pure procedures are procedures that have no side effects. A pure procedure simply maps from inputs to outputs using local data, right?
There's an atomicity. I think it's the term in like Haskell's
like
community is atomicity.
Yes, and I'll have to think some more about exactly what that means, but I know you're right. The atomicity, I guess, is related to
like how isolated your inputs are from your outputs.
Yeah, exactly. Right. So isolated in the sense that you're not able to do things like write to disk, I guess, and really. Well, okay. Oh, that's interesting. Okay, I haven't done any Haskell programming. I probably should.
It's actually very good.
Awesome.
Is there a vector cross product or curl term that's available in this?
Oh, by the way, okay, so in Fortran, when you write your own operators, you bracket them with a dot. So I don't mean to imply that the language provides you a gradient or a Laplacian.
Oh.
What I'm simply saying is that it gives you a facility for writing your own, and I'm also saying that expressiveness is really powerful because people can read the equation and know the type dynamics, right? Yeah, so these are all, which I will say though, this is unique to Fortran. So for example, or I'll say uncommon amongst languages. In C, you can't define operators yourself. And in C++, you can overload the existing operators. So you could change the meaning of a times or a negation. But in Fortran, you can also define new operators, and you can't do that in C++. So this is, the ability to do this kind of thing is really unique to Fortran amongst common languages.
It'd be cool if you have the old way of doing it, just to see.
Oh, yeah.
I like to have seen it.
Yeah. And so the other key point then is, since the Fortran 2008 standard, Fortran has been a parallel programming language. And so everything I'm talking about here, so this is a time derivative. If any of you have written any LaTeX documents, you probably use the underscore as for like subscripting. So think of this as like u sub t and think of it as a time derivative. And, the idea is that these objects, each of these things can be an object that is distributed across three-dimensional space. So what you're seeing here is actually a lot of computation. You're seeing, computing on a data set that might be, billions of grid points. So, and those distributed objects will be distributed across processes, which might be distributed across cores, which might be distributed across nodes on a supercomputer. So what you're really seeing is parallel algorithms operating on distributed data, and this is what drives it. So
This might be too much in the weeds, but when you do something like this, because I haven't seen this syntax before, I've never used it, I should say. I've seen it in your other talks. But when you do something like .Laplacian.u, the result of that's being combined with the other terms of the equation, is it allocating like a new array of the same size as u to return? And then allocating those automatically once the line is done being computed, or
so again, since these operators you implement yourself, you can make decisions about things like that. I would say, at least naively, that's how I'm doing it now, because the biggest thing for me is I've just been trying for so long just to even get this approach to work.
You can return the same array you put into the operator if you.
Well, so I could imagine an approach where you could use pointers to be smart about the memory allocations so that you don't have to have new memory being allocated all the time. But I'm a good ways away. Once I can even get that expression to fully work and be, run a distributed memory, automatic GPU offloading, I'm 58. So probably by the time I even get to that point, it's gonna be time to retire. But certainly if I do get if I do get all of that working, then yes, one of the things I'd like to explore is getting even more sophisticated about the memory management. Because if I leave it to the compiler, then yes, it's gonna do a bunch of new allocations all the time, and that can hurt performance. So I'll quickly run through a bunch of different packages that we develop and, kind of how they leverage this modern Fortran, leverage and support this modern Fortran ecosystem. Caffeine, Julienne, Matcha, Fiats, FPM, I'll just kind of get to them when I do. So Matcha is, I have a collaboration with David Torres at the Northern New Mexico College, and he was funded to work with me through a program called Sustainable Research Pathways. And David was interested in modeling basically these random walks of T cells as they move through human tissue. And one of the things that can happen with the T cells is that, so when he's modeling them, he typically treats them all as completely independent, but they can actually communicate with each other, and they communicate by releasing species like something called a cytokine or cytokine. If you go back, COVID during the pandemic, a lot of the deaths that we saw were caused by what's called a cytokine storm, basically releasing too much of this stuff. But what happens is that the T cells can then move up gradient, basically, and find like a point of infection, right? So you need something like a diffusion equation to model the diffusion of the cytokines. And so that's what we have here is, writing out a diffusion equation. And it took me, I love acronyms. It took me 2 full weeks of work to come up with an acronym that has TC in it. Motility. So motility is what doctors call for motion, used for motion. So motility analysis of T cell histories and activation. And then the compiler will take, if you're using the multi-image features, it will take your code and compile it down to ultimately what ends up being calls to caffeine, which my group develops as well. So so the multi-image features started off as a separate language, like a spin-off, and it was called co-array Fortran. So caffeine is the co-array Fortran framework of efficient interfaces to network environments. And I love that caffeine uses Matcha, or at least it will. We're not quite far enough. We actually just got the first multi-image features into playing, at least within the past few weeks, like one of them just today even. So we're not quite yet to where caffeine has enough features to actually support Matcha yet. But this is still kind of like the dream that I'm chasing. And under caffeine is GasNet-EX. The EX is for exascales, like 10 to the 18th floating point operation per second. So this much I at least have working. So I haven't gotten to the full Navier-Stokes equations, but let's say if I want to solve the heat equation. And right here, I'm just writing out a simple Euler, explicit Euler time advancement scheme. So I've got this Laplacian operator implemented to operate. I'm using T here because the diffusion equation is like the heat equation. So you could think of this as temperature if it's the heat equation, or concentration if it's the diffusion equation. So that much is working. And I can do that and across multiple images. So you can imagine taking a domain and partitioning it up so that there's, like, in this case, maybe 3 subdomains, and then you have these halos in between them where you could think of them as like outboxes and inboxes. This is how the different subdomains communicate with each other. Now, it turns out, though, that the bottleneck in this code is where we're computing the Laplacian. But I'm doing it with do concurrent, so you can see what a do concurrent loop here looks like. Dan Nagel, who used to lead the American Technical Advisory Group, basically the US subgroup within the Worldwide Fortran Committee. He said to me a while back, the philosophy of Fortran is to give the programmer the ability to communicate properties of their code without necessarily having to mandate what the compiler do to exploit those properties. So what I'm saying with do concurrent is I'm saying the iterations of this loop are independent. There's no data dependencies between them, where one is defining a value that the other iteration needs. And therefore, telling the compiler, have at it. Like, if you want to parallelize this, run it on vector units on the CPU or multi-threaded across multiple cores or offloaded to a GPU, that's all a compiler-dependent decision. And now you wouldn't want, the compilers aren't magic, so you wouldn't want to give them all those options and let them choose. But what you do is you just pass a flag. So there's one flag you're going to use if you want to multi-thread, a different flag that we'll be using when we're ready to start doing GPU offloading. But the point is that the source code itself won't change, right? So I used to teach a course at Stanford. It was a graduate course on my book. And I taught it 3 times. By the 3rd time, I had decided that if you have a parallel programming model that's sufficiently clear, why write serial code at all? Like I actually think we could start teaching programming as parallel programming, right? Because there's nothing really that's that much more hard about this than writing a regular do loop. A regular do loop, by the way, is explicitly not serial. It's explicitly serial, non-parallel, meaning one iteration happens after the other, right? And it has to be that way. What if you're doing something like time advancement? You can't compute, the new time before you compute the old time. So it has to be serial. So what we do, the pattern that we've all developed is we write serial code, and then we come back and tell the compiler, oops, I lied. I don't really want that to be serial. I want you to actually do it in parallel. And we do that with OpenMP directives or OpenACC or what have you. I say, oftentimes people think, how can I parallelize this algorithm? I turn that around and say, why would you ever serialize it? Like we could actually just write parallel code from the start. And you know where that came from, that idea, there's a professor, Peter Pacheco, I think he's retired now, but he was at the University of San Francisco. And he wrote a book on parallel programming, and he used C because he wanted a small language, that he could teach the students fast. And his textbook was designed for sophomores in college. As I think it might have even been like as their first programming class, or certainly maybe not first, but second, maybe. Like, I think we could push parallel programming. That when I was in grad school, you were like, if you were doing parallel programming, you were like a PhD student in computer science, like not even in any other field. Now I think we could push this stuff all the way down to the sophomore level. Actually, someone has done it at the sophomore level. But he was using MPI and OpenMP. I think it's even easier if you do it the way that I'm describing. So these are results from TAO, the parallel performance analysis toolkit. And basically what it's saying here, there's this line 188, which is, C is 188. It's basically telling me that like that one line takes up more time than any other line in the whole program. That's what that whole graphic is about. Okay. In our software stack, we've been developing Julienne. Julienne vegetables are vegetables sliced into thin strings. It's actually inspired by a package named Veggies, and it was originally designed to be a lightweight, more portable Veggies, so that's why we named it Julienne. Over time, it has taken on some features that I think now make it compelling in its own right. So it's no longer just a lightweight Veggies, but it also has lots of string manipulation features in it. So the analogy, just stringy vegetables, still kind of applies. And you can use it to write unit tests that test your code. So I think of unit tests as being external to the code. Or you can use it to write assertions. Assertions are checks that you put inside your code, where basically you're asserting certain things that you expect to be true, because if they aren't true, then there's nothing good that your code can do. And then the compiler will basically stop the program at that point if the assertion turned out to be false. So you can use Julienne for unit tests and assertions. Did I see some hands go up? No? Okay. I think since we've been having questions all along, I think I'll maybe just use the full hour, but so jump in if you have a question that you haven't asked yet. Just go ahead.
Is Julienne's Fortran specific, or I mean, if it can be done outside the code, is it Fortran specific, or is it more?
Yeah, it's Fortran specific. Okay. Yeah.
Does it get confused for a Julia package now then from the name?
Yeah. So it is Fortran specific, but it doesn't place any requirements on the Fortran code in terms of so you could use it to test Fortran 90. Like it wouldn't have to be anything beyond that. Okay, so this is a slide I showed earlier where I was highlighting this expression down here where I'm advancing the heat equation. And up here I'm comparing a functional style of writing the solution of computing the solution to a more traditional procedural style, which I don't show. What Julienne does is it gives us a set of idioms for writing correctness checks, right? So I came across this phrase a while back, idiomatic Python, sort of like if you're writing Python in the way that someone who really knows the language would write it. And I remember at the time thinking, man, I wish I had an idiomatic Fortran, but then, you know, who would I be to define idiomatic Fortran? But then when we were working on this stuff, at some point I realized, oh, we're defining idioms. This is idiomatic Fortran. So idioms are common phrases, you know, common turns of phrase or ways to say things, right? And, you know, you can kind of imagine what this means. It's saying all TF approximates, I guess for better English, I should drop the S, all TF approximates TP within tolerance, right? So that's a natural language, natural English sentence, which by the way, I don't know if we're gonna have much time to get into it, but I have a couple slides that I think we probably won't get to. One of my punchlines here is that, how many of you know the term vibe coding, or anybody not familiar with vibe coding? No? Okay, so natural language prompting. We have this idea that we've been exploring of what we're calling idiomatic vibe coding. So one of the big problems with vibe coding is that the English language is ambiguous, right? And one of the important things about programming is that you need clear definitions of things. And so in this case, Julienne defines these operators like all, and Julienne defines approximates. And the whole syntax is backed up by a 700-page standard that defines the syntax and the semantics, right? Including the formal definition of the syntax. And so the idea of idiomatic vibe coding is to introduce tests into as part of your prompts, but to write your tests with Julienne so that you're still getting to write an English sentence, but you're writing one that's well-defined, right? Our experiments with it so far are that it can improve things some, but I'd still recommend against vibe coding other than for fun. Yeah.
Test the diagnosis
Yeah.
and make it appropriate within tolerance,
Approximate.
carriage return,
Yeah. So,
and then it does it.
yeah,
I
so
think
the idea,
you need you need keywords, you need reserved words for that. So you need a reserved word for, if it's an English compiler,
so,
literally,
yeah,
period, end of story. You need that.
yeah, so again,
reserved words.
as I was saying earlier, when you write your own operators, you bracket them in dots. So what you're seeing here is operators that we've written in Julienne. So there are no reserved keywords involved here. Now, what's really cool, so those of you who have written some Fortran, how many of you know about elemental procedures? Nice. One of the most useful features that so few people use, and it's a feature from Fortran 95. It's 30 years old. Okay, so this is gonna, those of you who aren't familiar with it but have written Fortran, this is gonna blow your mind. Like you gotta look at what's in the language. Reach out to me if I can help. If you take a procedure and make it elemental, that means you write the procedure as if all the arguments are scalars. But at runtime or at compile time, you could pass in not just scalars, but arrays. Fortran has multi-dimensional arrays, which by the way, C still doesn't have, and C++ just got 1 or 2 standards ago. And with Fortran, the arrays can be of dimension 1 through 15. I guess maybe they were thinking of like superstring theory, you know, 11 dimensional spaces or something. And so I write that. So when I write these operators, almost all the operators in Julienne, so all is actually one exception, but almost all the operators in Julienne are elemental. So when you look at this, it could either be a scalar, or it could have it could be an array, and it can have dimensions of 1 through 15. So it's 16 different cases that are all being handled by the compiler by me just writing one implementation of that operator.
So kind of like the dot operator.
So are you talking about like a dot product or what?
No, so like if you have some matrix
Mm-hmm.
in MATLAB,
Yeah.
and you're doing some operation on it, and you follow that matrix with a dot.
Yeah.
Say you wanted to square all elements in the matrix.
Nice. Yeah.
You follow a dot.
Yes.
Like
Yes.
Dot caret squared, that gives you
Yeah.
elemental.
Yeah,
as
exactly.
opposed to-
Yeah, it's been a really long time since I've written any MATLAB, but I do know that a lot of the features in Fortran are modeled after MATLAB. But what happens, of course, is that since it's a compiled language, you'll tend to get much better performance, right?
Yeah.
So in other words, remember, this could be like a three-dimensional Laplace I'm evaluating. So in other words, this thing could be a three-dimensional entity, a three-dimensional array. I get to write that one expression, and Julien's going to go through the whole array and see if anything is outside of tolerance. And I'm only going to get diagnostic error messages on the ones that are out of tolerance, right? And then I can use this all operator to aggregate all the results. What that does is it packages them all up into one object, and the object is of type test diagnosis T, is the name of the type. And a test diagnosis T object has two things in it. One is a logical, or in other words, Boolean, that tells you if the test passed or failed. And the other is a diagnostic string that gets constructed automatically for you, right? And it gets constructed with knowledge of the sentence that it came from. So it will say, here's the actual value, here's the value of TF, here's the value that was expected, TP, here's the tolerance, right? It'll give you a nice diagnostic message. Yes?
Yeah, if you use approximates, it's an English word, but the domain is something related to unit testing or doing something.
Right.
It's not the actual, it's a subset of the English word approximates.
Yes, yes. And that's important. Context matters so much, right? The fact that there is a larger set of ways that you can use the word approximate is the problem with vibe coding, right? That just really underscores it right there. So we developed something called the parallel runtime interface for Fortran. It's actually not software, it's a set of interfaces. And what it means is that a compiler that takes your Fortran and lowers it to implications of these, or targets this pref interface. Any compiler that does that can use any runtime that supports pref, right? So you could make basically a link time decision to swap out caffeine, which uses GasNet, and choose something else that uses OpenMPI. Hypothetically, that's where we see things headed. So with my final 3 minutes, that was a little more traditional HPC. We also do deep learning with all Fortran all the way down. We have a package called Fiats, functional inference and training for surrogates. Surrogates are a type of neural network or way of training neural networks to substitute for something. Also think of it as Fortran inference and training for science. Also a fiat is like a decree from a dictator. So kind of, maybe we shouldn't always believe everything we're getting from AI. So why would you use something like this that's all Fortran all the way down? One of the things is that it buys you certain things that you can't do with other solutions, like PyTorch with Python, or even the C++ API that has a PyTorch, has a libtorch backend, is that almost every procedure in Fiats is pure. So I talked about pure procedures before. What I didn't mention earlier is that with that do concurrent construct, if you call, the block that I showed you didn't have any function calls in it, I don't think. If you call any function inside do concurrent, it has to be pure, because pure programming, pure functional programming makes the parallel programming so much easier that the compiler can do a lot of it for you, right? So for example, you can do, if you're doing inference, these are a couple of cases where we've used, we've trained a neural network to match something from a cloud microphysics model. We've also done inference on aerosols. You're seeing like the results of the surrogate model on one side and the actual computation on the right. And what I can do then is I have some neural network object, and I call this infer procedure on that object, pass in some inputs, and I can put that instead of the usual approach, I can drop it in a do concurrent, where there's no ordering between passes through this loop. With OpenMP, I've got to tell the compiler, not only that I want this serial loop to actually be parallel, I've also got to tell it to collapse the loop. Whereas here, it's fully collapsed. With elemental procedures, I can go even further, and that basically becomes one line, right? Because I can pass in, instead of each element, this is an object, but it's a 3D array of objects. Instead of passing in each element of that 3D array, I can just pass in the whole thing, because I'm choosing elemental, right? Go back and think about it, all the code that you've written where you were looping. Like, this is what, like, people think of Fortran as being this ancient thing, when in fact, in some ways, it's so far ahead. Like all these other languages, why are we writing loops? Loops were in Fortran 66. Loops are a 60-year-old technology. So somebody tell me again, like why everybody thinks Fortran is behind and Fortran is old. You can't do that in C++. I guess you can do it in MATLAB. That's cool. Thanks for telling me about the dot operator. Okay, I think I'm pretty much done. What's that?
Not that well.
Oh, I'll get to you in 1 second because I'm out of time, but you know, I'll just say that we basically get the same performance out of the concurrent that we would out of writing our own OpenMP. I wish I had time to talk about the Fortran package manager. I tell people like how many of you have used Makefiles? Okay, how many of you have used CMake? Okay, you don't have to put your hand up. I wonder how many are in therapy. Oftentimes tell people, you switch to Fortran package manager, you won't need therapy anymore. Like it will change your life that much. So Fiats is the full software stack is about 17,000 lines of code with like 2 external dependencies. This is my entire build system. If you use the Fortran package manager, this is it. You tell it your dependencies. Now, in this case, I wrote the dependencies, so they're also FPM projects. It's going to go out, download them, build them, link your code to it. You're done.
Is it possible to show the previous slide? There's the
Oops, sorry. So the idea is that with Makefiles, you specify your files, you specify your dependencies. With CMake, a lot of people don't know this, that you really should also be specifying your files in CMake. And CMake will discover the dependencies. FPM does you one better. You only optionally specify where your files are located. You don't name the files at all. But if you use certain default directories, then you don't even do that much. It's just going to find all your files. It'll discover all the dependencies. You're done. I think I'm out of time, but I'm happy to stick around and answer any other questions anybody likes. Yes, I'm sorry.
Okay, a lot of us are actually just starting with Fortran, like this week in a class. Is there anything that?
What class?
Comp 526, it's computational methods of sciences.
Who's teaching it?
Dr. Valeria Barra.
Barra?
B-A-R-R-A. Is there anything that you wish people knew when first starting Fortran, especially now when we have all of this?
Oh, well, it's elemental.
Yeah, but like anyway, don't do
Great
this.
statements, elemental, do concurrent.
Got it.
Don't ever use common blocks, don't use data.
You don't need to write loops in so many cases with Fortran.
Okay.
The other thing I'll say is that and unfortunately, and there are some fairly good books on modern Fortran. The standard is not that easy to read in general. But the number one thing that I wish most people read in the standard is the list of intrinsic functions, the function the language provides you.
Like the standard library.
Yeah. I could show you an example inside Julienne where I do something in 2 statements. And just as an exercise for one of my group members who was going to give a presentation, we thought this would be a fun exercise to do. I took those 2 statements and I rewrote them in the way that most people currently write Fortran. It expanded to 36 statements.
Wow.
But to do it the way I do it, you have to understand array statements really well, and you have to know about the intrinsic functions of the language.
Like, there's a map mall that does one matrix multiplication between two arrays. Like, that's a whole algorithm in one line.
If anybody needs to leave, please feel free to leave because I know we're past time, but I'm happy to hang around.
Oh, so this is great. So, I write lots of Fortran code, although most of this, so.
I learned Fortran in your class.
Yeah, so I have 2 questions. So I admit I tend to write older Fortran because I write open source code that I want people many different places to write. So what's sort of the spread of more modern compilers? Because it's hard to know, well, if I use a more modern thing, will everyone get caught up? Because, you have to pay for new compilers and you may have a 20-year-old compiler on your thing.
Yeah.
And the other question is, what about performance? Because at least again, writing older Fortran, I found in my real core code, going from an array in a derived type to just a plain array, sped it up by a factor of 2. That may not be true with more recent standards, but those are the question.
I mentioned earlier, I'm trying to design patterns. Okay, so, and you're putting it inside a direct type, that means you're putting it in an object basically, right? You're doing object-oriented programming. So object-oriented programming is the mechanics. It's how do I put data inside this type? How do I attach procedures to that type? Okay, that's the mechanics. Object-oriented design patterns is which types should I write, right? How should I group the data? Most of the problems that I find that people have with object-oriented programming are actually problems with object-oriented design. So what happens is when we first learn about objects, and honestly, I've been doing object-oriented programming for close to 25 years. And I still honestly would say that it's only been within the last 3 or 4 years, I feel like I really got this down now. So I'm sorry about that complexity of it. But mostly we go around and we think like, well, there's all these objects there's all these things that could obviously be objects. You know, like if I'm writing a finite element code, obviously I want to have an element object. Maybe not so obviously. Because if I do that, then I'm going to be writing a bunch of loops that are working on a small amount of data that's going to cost a ton of time, when what I probably should be doing is aggregating that into a much bigger object that has, you know, a whole field or a whole subdomain of a field in it. So yes, you can definitely run into problems just from putting something in an object, but it probably has a lot more to do with how you chose to break things down than with the fact that you put it in an object. Right. So
sometimes it could be intrinsic, like in GPU kernels, the hop to get to the array.
Yeah.
On a smaller kernel can have launch overheads that are bad compared to. But the thing is, you can still use it. You just have to pass it in as an array to the function, and then the compiler doesn't have to do the hop anymore in the kernel. So there's a ways. Yeah. Sometimes when it goes slow, there's other ways to like. Yeah. Still use it and still get your performance too, depending on the compiler. But
so that's it. Basically what I'm getting at then is it's kind of orthogonal. Like you can write really high performing object-oriented code, or you can write really low performing object-oriented code, and the same is true if you're not writing object-oriented code. But I feel your pain. I understand. Yes.
How do you load up Fortran 2023 on Macintosh?
Okay, so any of the software packages that I mentioned, with the exception of FPM, we have a short URL, go.lbl.gov. So if you just put the name after that, go to lbl.gov/Julienne or go to lbl/matcha. I would say check out the Julienne repository. We test with four compilers, and in most cases, multiple versions of those compilers. So basically, it really depends on, let's say my recommendation would be go with Flang. And the latest version, Flang 21, supports probably almost everything from Fortran, 2023 that you would actually care about for the most part. And the rest is coming really soon. And it's going to have the fewest bugs in my experience. So there are only 2 compilers I know of that fully support the whole Fortran 2023 standard, and those are the Cray compiler and the Intel compiler. But
which one?
Cray from Hewlett Packard Enterprise HPE. Yeah. But both of those are way buggier than Flang. So I would start with Flang, and if there's a certain feature that you really need that's not there, then maybe you jump to Intel. Intel's compiler is free now.
It's impossible to install it on a Mac.
Exactly.
You can't run Intel or on a Mac.
Flang is the way to go, and you can install it with Homebrew.
Is GCC like the newest GCC that's not fully compliant yet?
It has everything that I think you're going to care about, honestly. Yeah, I mean, I
know they didn't have like do concurrent reduce for a while, but like I don't know what they are for the next or something.
So I started a business called Archaeologic because we do software archaeology. We dig through old codes and update them. So I've spent a lot of time looking at other people's code. So I have a very good understanding of what's out there. And unless you're doing something, really unique that I haven't seen, you're going to have a hard time finding anything missing in Flang, with one big exception. And the big exception is the multi-image features. But like I said, my group is working on that. And we've actually started to get them upstreamed into the LVM project repository so that even by the time of Flang 22, you'll start to have those features too. And I know that most people aren't using those features. So that's why I can safely tell people anything you want is there. Are you using co-arrays at all or multi-images?
No.
Exactly. So without even asking you, I know that everything is that you want is there.
But well, I mean, co-arrays are only supported, I think, in G4tran with OpenMP underneath and with Intel with MPI underneath.
So G4tran supports co-arrays with open co-arrays with not OpenMP.
Right.
Yeah, right.
Yeah.
And then what was the other one you said?
I think Intel has an implementation, right?
Intel.
I've never
HPC.
seen actually any like scaling plots of anyone using co-arrays on these different compilers though, so I don't know how good they are.
No, it's it depends on what you're doing. I mean, in theory, it actually could be faster. And, okay, so these questions get kind of complicated because MPI has been around for a long time, and most people are still writing old MPI too. So, are you writing an MPI?
Yeah.
Okay.
And we don't touch the MPI much anymore, but
Okay, and there's a 95%. I'm gonna give myself 95% odds on this. Are you using two-sided MPI with sends and receives, or one-sided MPI with puts and gets? 95%.
in between, I said I received.
That's wait. Oh no. Okay, sure. I'm including that, but you're not doing any.
Quick get, but we're doing.
Okay.
Not blocking.
I could have guessed that before I even asked you. Okay. The puts and gets oftentimes will give you better performance. Okay. What's happening if you switch to co-array Fortran, if you switch to Fortran's own native features, and let's say you're using G4tran, which then means you have to link in open co-arrays, you're getting one-sided under the hood. You didn't have to write it yourself. And trust me, one-sided MPI is much harder to write than two-sided MPI.
It is.
Yeah.
I don't do.
So from that perspective, so the question is, how do you do the comparison? Like, people are wondering, okay, am I going to lose speed if I switch to co-arrays versus? Well, first, let me ask you what kind of MPI you're writing. Because what's going to happen is we're going to give you better MPI than you would have written.
If you had written that, it might be the same.
Sure.
Right.
Yeah. So it's a question, right? So if you let's say open co-arrays was using two-sided MPI, sends and receives, right? Then of course, there's no way I can offer you better performance compared to your own two-sided MPI because you're having to do procedure calls, through a software stack to get there. There's going to be some hit. But we don't do two-sided, and nobody over here who's writing their own MPI is doing one-sided. So there's actually a reasonable chance you might get better performance by switching. Yes.
Yeah, so if I like the syntax of the do concurrent, right? When you say that line supports do concurrent, but other compilers may not, can other compilers like G4tran still recognize the syntax, but maybe not do any of the offloading? Just if you just solely want the concise syntax.
Yes, that's exactly the world we're living in right now. That G4tran accepts the syntax, it just doesn't do anything special with it.
We just had a paper last year of the portability of do concurrent across compilers. So basically, every modern free compiler will at least not
until 3 weeks ago.
Yeah, it won't not compile. Like it will compile it on G4tran. You're going to get serial, but
Well, so okay, in terms of supporting do concurrent, the Cray compiler, the NAG compiler, the Intel compiler,
NVIDIA,
G4tran, NVIDIA,
all of them.
and Flang. So they all accept it. Now, which ones will actually do something special with it? The Cray compiler can actually offload it to a GPU. NVIDIA can offload it to a GPU. Intel
Flang says they can.
Yeah, and Intel can offload it if it's an Intel GPU.
Yep.
And Flang 21, which just came out about 3 weeks ago, can at least parallelize it. It just can't offload it.
I think a lot of the other ones could do CPU also. So CPU.
Oh, sure. Yeah.
I think G4tran is the only one that doesn't.
Yeah. So 5 of the 6 compilers I just named can at least parallelize it, and 4 of the 6 can offload it.
And most of those are free.
Yeah, exactly. The only one I named that's not free is NAG. You have to pay for that.
Yeah.
You could effectively say the Cray's not free because you have to buy Cray or have access to it.
Yeah, but the NAG compiler says that it's up to 2008, and it has some features of 2018.
That's what NVIDIA says too.
Yeah.
They don't have all the things.
If anybody's looking for like a class project or something and you want to get involved with the stuff that I'm doing with OSA, we just got going on implementing the mimetic differences using this style that I'm describing. So I just submitted my first pull request against Mole to add some Fortran code in there. It's not doing anything useful yet in terms of numerics. Right now, I'm just kind of getting the object-oriented design. Like, what are the derived types we want to write? You know, what's going to go inside them? I'm getting the testing set up with Julienne and the building set up with FPM.
Latest
sorry, one last thing.
Macintosh.
Despite the name, Fortran Package Manager FPM, it can also build C and C++.
Nice.
Yes, there's a package, you won't need therapy. I'm sorry. There's a package called Super LU that's developed at Berkeley Lab. Not that I know, not that I'm guessing you're in therapy. I'm in therapy, even though I use FPM. There's a package developed at Berkeley Lab called Super LU, the linear algebra package. It's 32,000 lines of C code. I have a Fortran project I'm working on where we want to use Super LU, so I contributed a build system, an FPM build system. It was just like what I just showed you. It was 3 lines of code. It's building 32,000 lines of C. Yeah. Only thing I had to do in addition to that was to create a soft link. That's it. I was done. I'm sorry.
Oh, no. It's the latest Macintosh is 32 core GPU cores, and I'm assuming they're
The MPIs.
ARM.
Yeah, they're not, but yeah, ARM-based.
ARM-based.
ARM-16.
But would anything offload to an ARM-based CPU? I mean GPU.
Well, so the Flying 21 feature, you know, it's just translating to OpenMP, so it can offload to anything that OpenMP supports. If so, it's not really, even though the features were written by AMD, it won't only work on AMD. It should work on any GPU unless there's just no OpenMP support for offloading to that GPU. Okay.
But I will say that the M chip has a unified memory structure, so like this high bandwidth memory is on the CPU cores of the M chip. So if you compile it to concurrent on GCC, for example, and you if you do the multi-threading on GCC, which is a flag you can do, it will take advantage of that high-speed memory on the cores of that M chip and actually give performance close to GPU sometimes. So it can work, but it's tricky. Like it's not, because there's not so many compilers that are max supported right now. So probably the LLVM, if it has the CPU to concurrent, it probably would work fantastic on there.
Yes, but then they have GPU cores.
So those cores, I don't know of any way.
If anybody wants to try the Fortran Package Manager, also it's the easiest package in the world to install. Oh, the Fortran Package Manager was originally written in Haskell by Brad Richardson. He used to work for me. He did it to learn functional programming. He tossed it out to the open source world. A bunch of Fortran programmers liked it, but nobody knew Haskell, so they rewrote it in Fortran. The Fortran Package Manager is written in Fortran. So Fortran is moving into new domains, not just weather, climate, nuclear energy. One of the coolest things I've ever seen, every time they produce a new release, meaning it's just this big open source community, you know, every time there's a new release of the Fortran Package Manager, you go through all the, you know, release assets. One of them is a single file that has all of FPM's source code concatenated into one file. So it's currently about like a 47,000 line file. You compile that one file, you have a working installation of FPM, you're done. So you can install it with Homebrew or I think APT on Linux, or just compile that one file.
Is there pip install too or something? I remember like.
I would be well, yeah, I don't know.
I don't remember.
Maybe.
I thought it was even easier on some systems to install it. So I installed it once and it was like single command or something to grab it.
Yeah, like with Homebrew, it's just brew install FPM.
Oh, it's actually in brew directly? Oh wow.
I'm the one with the bug where that Homebrew crashes if it's older than Big Sur on the Mac.
Oh, interesting.